they are related to the machine learning techniques. And then we will talk about the unknown functions, and after that we will talk about the training and selection of different machine learning models. Okay, so the basics of machine learning, so that are help us to select the different machine learning models, and for those models we will perform the training. And after that we will talk about the design issues of a machine learning system, and finally we will see an example of machine learning system, and we will see the different components, how the different components are interrelated in a machine learning system. So we will also see that. Now, if we try to understand what is learning and how this learning can be incorporated into a machine learning system or just a learning system, so we can take an example of a person identification. Okay, so in person identification, what we humans do, we can when we see a face of a person, so we can identify that person by their face as well as by their name. But name is not important here. If we remember the face, then obviously we may or may not be remember the name. Okay, so since the humans have the cognitive abilities, so therefore this, when we want to incorporate these cognitive abilities into a machine learning system for person identification, then that machine needs, or the algorithm which run on that machine needs the learning experience. Okay, so how this learning experience is created. हेलो सबमिट करना है हेलो और कल वो भी सबमिट करना है ना Okay. So the problem of machine learning can be understood by a person identification, and when we see a person, so we can identify that person by their faces. Okay. Now, if we want to incorporate these cognitive abilities into a machine learning system for the same task, then we need to design a person identification system using some machine learning technique, and then that machine learning technique will be able to learn from the experiences. Okay, or learn from the different examples or different instances. So the same way we can understand the learning strategy in a machine learning system, and for that we need some basic terminologies. So these basic terminologies are related to the learning system. Now these basic terminologies include the domain, range, data, then loss or penalty, and risk. Okay, so these five different terminologies are related to any machine learning system. And when we consider a learning system, so we can consider a data set D, and again we consider the unknown function f, and this function is considered to be defined on this data set D. And considering this data, we can construct a good approximation of this function f, and this is called the learning. That means the learning is all about is nothing but to get a good approximation of the function. If we, so this function may be the known function, or this function may be unknown function, and this function is defined over D, and we have to determine a good approximation over this function f, and this is nothing but the learning. Okay. Now, the first terminology is known as domain. So what is domain? So here the set D is called the feature space, and an element capital X that belongs to D is called the feature vector or an input vector. Now in person identification, if you consider the problem of person identification, then person identification we use face image. Now from that face image, what we can do, we can extract the features, and this set of features are called feature vector. So if we are having 1,000 such images of different 1,000 peoples or different 1,000 individuals, then from that 1,000 individuals we can obtain 1,000 face images, and these 1,000 face images, from these 1,000 face images we can extract the feature vectors. Okay, so these 1,000 feature vectors will constitute the feature space, and this feature space is called the set D. Okay, and element X. So we can consider any random element in this feature space. So if it is denoted by capital X, then this X belongs to this feature space, and this X is nothing but the feature vector or an input. Okay, and the coordinates of X are called the features. That means here capital X is a set of features, and capital X here itself is a feature vector. Now the elements of this feature vector or X is called the features. Now the individual features may take values in continuum, a discrete, ordered set, or unordered set. Okay. So the features, the nature of features. Hello. Are you getting any problem? If you want to talk, log off you just log off this system. Okay, log off this meeting and then talk. Okay, the next terminology is range. So here range f of d is usually either a finite unordered set, and when the range is found to be either finite or unordered set, then the corresponding learning strategy will be called classification. Okay, so what is range? So range f of d is defined over range is nothing but a function f, and it is defined over the feature space d. Okay, now f of d is known as this range, and range may be finite and unordered set, and when such range is considered, then the corresponding learning strategy will be called classification. And when the range is found to be continuum, then the learning strategy will be called regression. Okay. Now an element capital Y that belongs to this range will be called a class in classification and response in regression. So here Y denotes the class information or the level, and when the Y belongs to this range, then this Y will be called the class in classification or response in regression. Okay. The next terminology is data. So data, we can draw the data x comma y from a probability distribution P on D by FD. Okay, so here D is the feature space and FD is the range. And if we take the multiplication of this feature space and range, and over this we can have the probability distribution P, and from this probability distribution we can draw the data, we can make the random draws of data x comma y. Now the data which are observed may either be consist of the domain range pair. So domain range pair means here the domain is x, so capital X is the feature vector, and x comma y, so and y that belongs to the range. So basically this pair of the components is known as domain range pairs. Okay, now the data which are observed that may either consist of domain range pairs or just domain values. Domain values means the the features in the feature vector. Now now when we have the domain range pairs in the learning in our learning system, then this is called the supervised learning. And in case of only domain values are provided, then the learning strategy will be called the unsupervised. Okay, so based on these two data that are observed can be used in supervised, either in supervised or either in unsupervised. Okay, so when the domain range pair is given or provided, then we can call the corresponding learning system supervised learning system. And when only the domain values are provided, then the corresponding learning system will be called unsupervised. Now in supervised learning, the the data which are arranged in the feature vector that belongs to that belongs to the uh, that belongs to the that belongs to the feature space, which is approximated by the range. Okay, so here tilted x is the data set, or we can say the feature space, and a over tilted x is the range. Okay, and when we get the multiplication of this range by feature space, then this is called the feature space is approximated by the range. Okay, now in this case we can get another component which is called the range, and this range will be associated with the domain value of the domain of the features value. Okay, so here x1 to xn are the coordinate points or features in the feature vector, and y1 to yn denote the label or the class information. Okay, so here from x1 to x1 y1 to xn yn are nothing but the domain range pairs in the feature vector. Okay, and here each xi comma yi is drawn from the joint probability distribution p of x comma y. Okay, so here p of x comma y is the joint probability distribution which is defined over x by fx, and such data are called the marked data. Why it is called marked data? Because in supervised learning we use the label data. Label data means the class information will be provided or label information will be provided. So if such data are drawn from the joint probability distribution p of x comma y, which is defined over this feature space, which is approximated by the range, then such data will be called marked data. Okay, so when we draw the data from joint probability distribution, so we can draw this data in two different way. Okay, so what are the two different way? So here capital Y, so this represent the range that belongs to the range. So this Y can be drawn from the range which is drawn from the range on f of x. Okay, and the data x can be drawn from the conditional probability p of x given y. Okay, or we can draw the data from marginal probability p of x. Okay, and we can draw the range y from conditional probability p of y given x. So in the former case we get the classification. That means we are interested to have the class information, and in the latter case we are interested to have the prediction in the regression. So the former case is known as the classification, that is the probability of y. So here we can write the joint probability distribution P of x comma y equals to the marginal probability P of y, which is multiplied by the conditional probability P of x given y. Okay, so this relation can be defined for the classification, and we can have another relation, joint probability distribution P of x comma y equals to, we can write the marginal probability P of x, which is multiplied with the conditional probability P of y given x. Okay, so this relation can be considered as the regression. So in regression, we want to predict the response, but in case of classification, we are interested to have the classification. So this y can be drawn from the range, if the drawn from the range, and the data can be drawn from the conditional probability p of x given y. Okay, but if we consider the unsupervised learning, then data can be arranged as x1 to xn, and that belongs to x. So here x1 to xn are nothing but the data points in the feature vector x, and such data are called the unmarked data, because in unsupervised learning the class information is not provided or class information is not used. That is why this x1 to xn that belongs to the feature space x are called unmarked data. And here the range f of x is assumed to be finite, in which case the unsupervised learning is called clustering. That means if the learning is determined to be unsupervised learning, then if we find that the range f of x is found to be finite, then unsupervised learning strategy will be called clustering. Okay, so if the range f of x is found to be in this range, so this is called the half closed interval. So first we this half closed interval, the starting point is 0 and the end point is found to be infinite. Okay, so if we write the half closed interval, then we have to write this third bracket. Okay, then we write 0 comma infinite. Okay, infinite symbol. So this infinity symbol will be closed with the first bracket. So this is nothing but the half closed interval. So if the range is defined in this half closed interval and the function f is to be learned with the mass or density function of the marginal distribution of the features, then unsupervised learning will be called density estimation. Okay, so we will talk about more on this supervised and unsupervised learning techniques, including clustering and density estimation. But for the sake of understanding the basic terminologies, those are used in different machine learning techniques. So we need to understand the interpretation of these basic terminologies so that we can understand each and every machine learning techniques in better way. Okay. Now, if we want to classify the learning problems, then we can classify the learning problems in two different ways. Okay, so firstly we can consider the range. Okay, finite range or continuous range. Based on that, we can divide the learning problems into two groups. And if we consider the observed range or unobserved range, so based on these two information, again we can classify the learning problems into two different groups. Okay, so firstly, we will consider the finite range and continuous range. So if we consider the finite range, so under this finite range, the classification and clustering will come. If we consider the continuous range, then regression and density estimation will come. Okay. Now, if we consider the observed range, so observed range, under the observed range, we can have classification and regression as supervised learning strategy. And if we consider the unobserved range, then under this unobserved range, we can have clustering and density estimation as unsupervised learning strategy. Now, if we can see this diagram, then we can see that logistic regression and neural networks. So here the logistic regression. Here you can see the logistic regression neural networks. So both these can be so these classification techniques can be transformed into regression problem. Okay, so there is an arrow here you can see from classification to regression over logistic regression and neural networks. So both logistic regression and neural networks are used as the classification techniques, but by changing the configuration of logistic regression and neural networks, we can obtain these classification techniques as regression model. So these methods are found to be common in classification and regression. In classification, we generate the class information or level information. In regression, we predict the response value. Similarly, if we see the unobserved range, so unobserved range includes the clustering and density estimation approaches. So if we want to find the relation between classification and clustering, then using so we can see that there is a arrow from clustering to classification, another arrow you can see from classification to clustering. So this cluster the arrow which is found over the classifier to clusters, then here we can see that since the clustering is the unsupervised learning strategy, so therefore no class information will be provided. So only here we only discover the pattern, required pattern, and if we want to associate the class information, then we can obtain the classification. Similarly, if we want to transform the classification problem into clustering, then we can use the nearest cluster strategy. So this nearest cluster strategy make the classification transform into clustering. Another unsupervised learning strategy or approach include the density estimation. So we can have the relation between clustering as density estimation, and this mixture modeling is found to be very common in both clustering and density estimation. Okay, and if we want to establish the relation between classification and density estimation, then we can have the several methods. These are called the likelihood methods, like linear discriminant analysis. So we can have the kernel density estimation, naive bayes. So these are the different likelihood methods. We can use these likelihood methods to transform the classification problem into density estimation problem. Okay. Similarly, we can have the few other methods which are very common both in regression and density estimation. So we can transform any classification problem to any regression problem by using logistic regression and neural networks as per the requirements. Similarly, we can transform the clustering problem into density estimation problem, as well as the classification problem into density estimation problem. So what about the machine learning techniques that we will discuss, which will come under these four approaches: classification, regression, clustering, and density estimation. Now another important terminology is loss or penalty. Now, how this loss function can be defined. Now, if we denote the loss function as L, then this loss function is specified. This the loss function denotes how the good approximation is obtained. That means if there is a function is provided, which is denoted by f, then we have to determine the approximation of that function f. Okay, now how good or how bad the approximation is, so that can be specified by the loss function. Okay, so if the approximation is found to be excellent one or the very good, then the difference between the actual function f and the approximation function will be very less. That means there will be a the deviation between these two functions, the actual function and the approximation function, will be very less. Okay, so deviations, uh, there will be a minimum deviation, so that can specify the approximation, that can specify the approximation quality of the function that has been determined from the original function of the given function f. Now if the loss function is denoted by capital L, then this function can be defined over the range f of x, okay, which is approximated by the new function f cap of x. So this f cap of x is nothing but the approximate function of original function f of x. So here f of x is the range. Okay, so we get another approximated function, which is another approximated function, and we are taking the multiplication. We are taking the multiplication between these two ranges and get the loss function. Okay, and this loss function is defined over the range R. Okay, now in this loss function, if we consider x comma y is a single point that belongs to the range which is approximated by f of x, then this loss function which is incurred by approximating y with f cap x. Okay, so here small x and small y. So here x is the data point, and y may be the function. So that belongs to the range which is approximated, that belongs to the feature space which is approximated by the range. Okay, now to define the loss functions, we can use different functions for regression as well as for classification. So for regressions, we can use two different loss functions which are known as squared error loss and absolute error loss. Okay, so in squared error loss, what we are doing, we are taking the square of the deviation. So if y is the original function, okay, if y is the original function and f cap of x is the approximated function, then what we are doing, we are taking the deviation between these two functions and then we obtain the square. Okay, so we are taking the, basically we are getting the square of these deviations. Now in absolute error loss, we are taking just the absolute value of this deviation between original function and the approximated function. Okay, we are not taking the square, no, square of the deviation, and both these loss functions can be used in regression for getting the prediction as a responses. Then we can have the 0 1 loss function. In the 0 1 loss functions, if we get a matrix as outcome, then in the square matrix, in the square matrix, we can have the diagonal values as 0, and elsewhere the values will be found as 1. Okay, so whenever we get the loss function as 0, that means the deviations are found to be nil. Okay, so the deviations are found to be 0, so that means the y is found to be the original function is y is found to be the approximated function. Now if y does not equal to approximated function, then we will get 1 in the corresponding locations in the matrix. So this 0, 1 loss function can be used in classification. So another loss function which is known as a cross entropy loss function. This cross entropy loss function can be used in classification. So if we define this cross entropy loss function, then this cross entropy loss function is considered the probability over approximated function. And here the conditional probability of p cap is obtained over y when x is given. So here you can see that small c, the value of small c varies from 1 to capital C. So the capital C is the total number of classes. Okay, and small c is used as the index for the number of classes. Okay, and here capital X is the feature space and small x is the feature point in the feature vector. Okay, so here capital X is the feature vector in the feature space and small x is found to be feature point or any feature in the feature vector X. Now when this feature vector is given, then we can estimate the class information as y for the classification. Okay, and here we are considering the original function y, and this is making the association with the conditional probability p cap of y given x. So in another way we can represent this cross entropy loss by taking the logarithm over this conditional probability, and that will give us the cross entropy loss for classification. Now once we obtain the penalty or the loss, or once we determine the loss function, now we have to reduce the risk. If the deviation is found to be very large between original function and the approximated function, then that means the risk is very large, and we have to minimize that risk as making the making the generalization error to be minimized. Okay, so here the standard criterion for good approximation of function a is one which minimizes the expected loss. If we are obtaining the expected loss, then it is our task to minimize the risks of that penalty or risks of that loss, and this is known as the generalization error or risk. Now usually the expectation is with respect to the joint probability distribution P on points x comma y that belongs to the feature space which is approximated by the range f of x. Okay, now the risks of approximated function at any random point x that belongs to the feature space x is the expected loss incurred by using this approximated function over the feature point, any random feature point x, in place of y for new data x comma y such that x equals to x. Now if we consider any random points in the feature space, so here we can write x equals to x, because this tilted x is the feature space, and if we are considering any feature point, so that may be equal to x. So previously what we saw that this x, which any feature vector, can belong to this feature space, this tilted x. Now we are writing x equals to small x. Okay, so therefore the risk of approximation at this point will be the expected loss which can be incurred by using this approximated function in place of y. Okay, so therefore what we are doing here, we are getting that is in terms of the expectation over this loss function L of y comma, this is the approximated function which is defined over this data point x. Okay, and over this loss function we are obtaining the expectation, and this expectation becomes the risk of this penalty function. Okay, so we can write in another form by taking the integration over this loss function, which is multiplied by this conditional probability. Okay, which is multiplied by this conditional probability p of y equals to this small y given x equals to small x. Okay, and here the range is defined, range is already defined. That means if we are having n number of classes that belongs to this range, then this n number of classes over this n number of classes, or using that n number of classes, we can get this integration over this loss function which is approximated by this conditional probability. Okay, because in this conditional probability we are interested to have the value of this y that belongs to this belongs to this capital Y given x, the random data point that belongs to the feature space. Okay, so the response variable y, which is treated as random with the conditional distribution. So here conditional distribution p, probability of y given x at point x. Okay, at random point x, while the input x equals to small x, and the trained classifier f cap are treated as fixed. Okay. Any questions from here? If you have any questions, you can ask me.
No, sir, no question.
Okay, I will send you this first 3 slides of these classes today evening. Okay, by today evening. So
Okay,
next
sir.
class will be held tomorrow. Tomorrow at 4:15. Okay.
Yes, sir.
Okay, that's all for today.
Thank you, sir.